Good day. I'm Norman Wobbeger. In this series, we are introducing a proper foundation for mathematics. We're proceeding carefully, step by step, one thing at a time, and we're going to move through the foundations of mathematics, creating proper structures, proper frameworks, so that the subject can be built up with confidence. We're emphasizing clarity. We're emphasizing precision of language. We're emphasizing the fact that we're not going to appeal to authority. We've got to understand the subject directly. We're not going to take anybody else's word for it. Today, we are going to look at an aspect of calculus that emerges when we just study very simple polynomials. Calculus is usually thought of as an advanced subject that you get to at the end of high school and then developed in the first and second years of college. For non-mathematicians, calculus has an aura of complexity and difficulty. Indeed, the modern treatment of calculus is in fact fraught with difficulties, as I will lay out later on. At this stage here, however, we are in a position to introduce some of the very basic ideas of calculus in a completely elementary and rudimentary way, based on the algebra of polynumbers or polynomials that we've developed so far. Last time we introduced the derivative and some higher analogs of it called the subderivatives. We're going to review that today, and then go on to start proving some important formulas from calculus. In subsequent videos, we're going to apply these to get highly non-trivial, interesting results. Okay, so we are working in the framework of integral polynumbers. A polynumber is really more or less the same thing as a polynomial, except it has a little bit more of an elementary fundamental aspect. A polynumber for us is a list of, in this case, integers, and this polynumber here can be written in this sort of polynomial form: 8 minus 5 alpha plus 4 alpha cubed minus alpha to the fourth. And here this alpha is a very specific polynumber. It's the simple polynumber 0, 1. So today we're going to introduce some calculus ideas applying to these integral polynumbers. We are certainly not going to use any limits, and we're not going to use any real numbers, and we're not even going to work in the framework of functions. We're just going to be talking about polynomials or polynumbers and the algebra of bipolynumbers. So a bipolynumber was an extension of the polynumber idea to include two variables, or a two-dimensional aspect. So we also introduced what we called a row polynumber, which is the same kind of object, except now it's written as a row instead of as a column. And then we had this sort of alternate notation using beta instead of alpha to tell us that we're going along a row. Beta represents the polynumber 0, 1 as a row. So by putting alphas and betas together, we saw that we could talk about two-dimensional arrays. They were extensions of polynumbers called bipolynumbers, and it's the algebra of these bipolynumbers in which we can introduce notions of calculus very easily. Okay? Without limits, without real numbers, essentially working just over the integers. Very important point. We're going to be introducing calculus ideas. So what we're going to be doing today really ought to be looked at very carefully by high school teachers and educators. This approach is very accessible to a year 9 or year 10 high school student, and will clarify and solidify a lot of their understanding of algebra. It's actually very fundamental kind of stuff. So perhaps some of you viewers will have just joined us recently. I do encourage you ultimately to go back to the earlier lectures in this series and to work your way through the subject. They may seem elementary, but there's a lot of content in what we've done so far. In particular, I'm going to review something that we've talked about already, Pascal's array, which has a very strong connection with calculus. Okay, Pascal's array was this pattern of natural numbers. And it's sometimes called Pascal's triangle. It has the property that, well, there's a rows of ones here, a column of ones, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Along here are the numbers we call the triangular numbers. Here are the pyramidal numbers. They have the property that at any stage, this one here is the sum of the one above it and to the left. And our indexing generally is considering this to be column 0, column 1, column 2, row 0, row 1, row 2. Now, why is Pascal's array important? Because it encodes for us the binomial theorem, which is a rule for expanding a binomial like this. If we have alpha plus beta to the 5th, we multiply that together 5 times and expand it all out, we're going to get these terms here. Various products of alphas and betas, all of degree 5 total, with various coefficients. And the coefficients are obtained from the Pascal's array by reading along one of these diagonals. We'll call this a diagonal of the array. So here is 1, 5, 10, 10, 5, 1, as the powers of alpha, say, decrease, and the powers of beta increase. At any one of these entries is sometimes called a binomial coefficient. So this one here is in the 4th row and the 3rd column, where our indexing starts from 0. It's equal to 35, and the explicit formula for it is that it's 4 plus 3 factorial divided by the product of 4 factorial, 3 factorial. And I remind you that 4 factorial means 1 times 2 times 3 times 4. All right, so that's a review of Pascal's array. Binomial theorem, very important, fundamental aspect of algebra. Okay, so let's go back down to a polynumber. Here's a polynumber, or if you prefer, a polynomial. 8 minus 5 alpha plus 4 alpha cubed minus alpha to the 4th. So the starting point is to look at this and say, we're going to think about this as giving us a bipolynumber, which we call the Taylor bipolynumber. And what it is, called T of P, is just the polynomial evaluated at alpha plus beta. So we're moving from one variable to 2 variables. We're going to replace each of these alphas with alpha plus beta. So we get 8 minus 5 alpha plus beta plus 4 alpha plus beta cubed minus alpha plus beta to the 4th. Now this has an interpretation as being a translate of the original polynumber by beta, if you like. And when we expand this all out and collect terms, obviously we're going to have to use the binomial theorem, because we have things like alpha plus beta cubed and alpha plus beta to the 4th. And if you did the exercise from the previous lecture, which I hope you have, you will probably have figured out that when you're expanding something like this out, it's very directly connected with Pascal's array. Because what we're doing is we're scaling the diagonals of Pascal's array. Why is that? Well, alpha plus beta, that sort of corresponds to this diagonal right there. Alpha plus beta cubed corresponds to this diagonal right here. And since there's a coefficient of 4 there, we're really going to want to multiply each of these coefficients by 4. Alpha plus beta to the 4th will correspond to this diagonal right here. We're going to have to multiply each of those terms by minus 1. So, intimate connection between the Taylor bipolynumber of a polynumber and scaling the Pascal's array in the sense of multiplying the diagonals of this array by the coefficients of the polynumber. This gives us a very efficient and effective way of computing this Taylor bipolynumber, and this Taylor bipolynumber carries inside it all the information about the derivatives and subderivatives of the polynumber. So it's a very important object. Very simple, but very important object associated to a polynomial. So let's have a look at that specific example, and what does the Taylor bipolynumber really look like? So the polynumber is 8 minus 5, 0, 4, minus 1, and here is the Taylor bipolynumber. It's obtained by taking Pascal's array and multiplying each of the diagonals by the corresponding coefficient of the original polynumber. So this top left entry is multiplied by 8, and then this next entry, which corresponds to alpha plus beta, is multiplied by minus 5. The next entry, which is alpha plus beta squared, corresponds to a coefficient of 0. Then alpha plus beta cubed got a coefficient of 4, so we have to multiply each of those coefficients by 4. And then alpha plus beta to the fourth had a coefficient of minus 1, so each one of these numbers is multiplied by minus 1. And there were no higher powers of alpha in the polynumber, so the rest of the Pascal's array, which in fact goes on indefinitely, is killed because they're all, if you like, multiplied by 0, all those subsequent diagonals. So this is the Taylor bipolynumber, and if we write it out in alpha beta form, then each of these coefficients gets associated to it a power of alpha and beta. The beta power is increasing in this direction, and the alpha power is increasing in this direction, starting from 0 in both directions. So let's make sure we understand that. So here is the thing written out, and I've written it out in kind of a diagonal triangular form to mimic what's going on here. So 8 minus 5 beta plus 0 beta squared plus 4 beta cubed minus beta to the fourth. Then the next row has power of alpha everywhere, so it's minus 5 alpha, 0 alpha beta, 12 alpha beta squared, minus 4 alpha beta cubed. The next one has alpha squareds, the next one's alpha cubed, and then alpha to the fourth. Well, we can write that out in a number of different ways. And one very nice way is to group together all the powers of beta with various coefficients, which are polynumbers in alpha. So when we do that, here are all the terms with no betas. Here are all the terms with a single beta, and then with a beta squared, a beta cubed, and a beta to the fourth. So I've just rearranged the terms that you find here in a line. And this then is the definition of the various subderivatives of the polynumber p. By definition, this is d sub 0 of p, this is d sub 1 of p, this is d sub 2 of p, this is d sub 3 of p, and this minus 1 here would be d sub 4 of p. These are the subderivatives of p. The zeroth one, the d sub 0 of p, is just p itself. So p is replicated right there. The first one, that's the zeroth one, that's the first one. The first one there, which we're calling d sub 1 of p, is sometimes just written d of p for short. And that has a special name. That's called the derivative of p. So there's p there. There's the derivative of p, which we also call the first subderivative. There's the second subderivative, the third subderivative, the fourth subderivative is minus 1, and the fifth subderivative and all higher ones are 0. Okay, so it's a very concrete, explicit way. We start with the polynomial p. We calculate p of alpha plus beta. We write it out, hopefully in a Pascal kind of form to make it very simple to understand. We're just taking Pascal's array, multiplying the various diagonals by the coefficients, and then we read off the columns are the various subderivatives of the original polynumber. So the connection between the original polynumber and its subderivatives is just the connection that we get when we multiplying Pascal's array along diagonals by the coefficients of the Pauli numbers, and then reading off things one column at a time. So if you have taken a calculus course before, I hope you appreciate how different this is as an introduction to the derivatives and the higher derivatives to what you usually do. It's a completely different story, it seems. However, the result is effectively the same. So this way of thinking provides a very interesting alternative to explaining calculus to high school students, almost to primary school students. It's so elementary, in fact, but let's not push it. A very good alternative. So just making sure, let's connect it now with a very familiar formula that you'll all have seen if you have taken a calculus course. Namely, what does the derivative of a polynomial look like explicitly? We'll give that a name. We'll call it the derivative theorem. And we're going to work with a general polynomial here, not a specific one. That's also instructive. Somehow the pattern is easier to see. So we're starting with a polynomial p, which is a0 plus a1 alpha plus a2 alpha squared, all the way up to a sub n alpha to the n. Or all the terms increasing powers of alpha up to alpha to the n. Then the claim is that the derivative of this polynomial, the first subderivative, which is the same as the derivative, is equal to this polynomial. And that's a1, that was same one there, plus 2a2 alpha plus 3a3 alpha squared, and so on up to n a sub n alpha to the n minus 1. And you can see the pattern most clearly if we just look at the nth term here. What's happened to the nth term? Well, the exponent n here comes down and is now multiplying the coefficient that was there. So instead of having a sub n as the coefficient, we now have n times a sub n. And also that power is decreased by 1. And the same pattern holds for all the other terms. For example, this one here, the 2 came down, multiplied by a2, and now we have just alpha to the 1. Here, the 1th power came down, 1 times a1, and alpha to the 0 is just 1. And this one here is a little bit special. It got completely killed. It's no longer around. All right, so let's just explain. Why is this true? It should almost be kind of obvious from what we've been talking about with the Pascal's array, but let's have a good look. So the main object is this Taylor by Pauli number. We're looking at T of p, which is p of alpha plus beta. By definition, that's d sub 0 of p plus d sub 1 of p times beta plus d sub 2 of p times beta squared, and so on. We're really only interested in this linear term here because that's the first subderivative or the derivative. That's what we're claiming is equal to this. So we have to have a look at this, and then we have to look at the terms which appear linearly in beta. So here's the Taylor by Pauli number. It's a0 plus a1 times alpha plus beta plus a2 times alpha plus beta squared, and so on all the way up to an times alpha plus beta to the nth. Now we have to multiply all of that out, and we have to look at what is the coefficient of beta. So, well, first of all, the constants, the things that don't involve any beta, are a0, a1 alpha, a2 alpha squared, all the way up to an alpha to the n. The things that do involve a beta are right here in this term here. So we have to go through where do we get betas from all these powers. The first beta that we get is from here. We get a1 times beta, so there's an a1 there. The next beta is obtained from this term. And you have to know the binomial theorem here. We get a beta when we multiply this out. There's a 2 alpha beta here multiplied by a2, so it'll be 2 times a2 times alpha. Times, of course, beta, which we've pulled to the outside. The next term will be a3 alpha plus beta cubed. And when you expand that out with the binomial theorem and say what's the coefficient of beta, it will be 3 alpha squared, and then we have to multiply it by the existing coefficient A3. All the way up to this one here, if we look at this and ask what's the coefficient of beta, well, that's the term that has alpha to the n minus 1 times beta, and that coefficient will be multiplied with an n from the binomial theorem, a single n, or n choose 1 if you like, and that n choose 1 gets multiplied by a sub n, and that's the term that we're getting there. And that there is exactly what we're claiming is the derivative. So we're comparing coefficients. Here the coefficient of beta is the derivative, so that's the derivative right there. And this is of course an important skill for all calculus students, is to be able to take the derivative of a polynomial. So if here's a polynomial, 7 minus 4 alpha plus 8 alpha squared minus 3 alpha to the 5th. So we have to remember that the constant term disappears, so the 7 vanishes. Minus 4 alpha, minus 4. 8 alpha squared, the 2 times 8 is 16 times alpha. Minus 3 alpha to the 5th. 5 times 3 is minus 15, and then alpha to the 4th. So all the same pattern over and over. The power gets multiplied by the existing coefficient, and then the new exponent is 1 less than the previous. Go through term by term. That's how you calculate the derivative of the polynomial. It might be useful to remind you of our notation for binomial coefficients. So in Pascal's array, the binomial coefficient n choose k, which is n factorial over k factorial times n minus k factorial. That's called a binomial coefficient, and that's the formula for the entries of this table. And specifically, here is the Pascal's array with numbers, and here it is with sort of the binomial coefficients. So along a diagonal, say there, the top entry is all 3. So here is 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. Those are the 4 coefficients involved in alpha plus beta cubed. Okay, so in parallel to the derivative theorem that we just wrote down, here is the second subderivative theorem, which tells you how to find the second subderivative of a general polynomial. So we're starting with the same polynomial p as before, and the claim is that the second subderivative, d sub 2 of p, is this expression. The first entry is a sub 2. So now the first 2 terms have disappeared, and now we just have an a2 here with no power of alpha. And then the next one is 3 times a sub 3 times alpha. And the next one, 6 a sub 4 times alpha squared. And so on to the last one associated to this is n choose 2. The exponent choose 2 times a sub n times alpha to the n minus 2. So the various multipliers that we're using here to multiply the existing coefficients are coming from this second column of Pascal's array, which we recognize as being the triangular numbers that we've talked about previously. The triangular numbers are appearing here as the numbers that we multiply the existing coefficients with to go from the polynumber to its second subderivative. The other thing to note is that the powers of alpha are decreasing by 2 at every stage. So from here, alpha squared to alpha to the 0, from alpha cubed here to alpha to the 1, from alpha to the n to alpha to the n minus 2. With the derivative, they were decreasing by 1. With the second subderivative, they're decreasing by 2. Corresponding to the fact that we're going over 2 in the Pascal's array. So the proof follows very much the proof of the previous theorem. We have a look at the Taylor bi-poly number, p of alpha plus beta. There's its definition, just as before. And there's what it amounts to for the polynomial that we're looking at. Our job is to find the coefficient of beta squared in here. So we have to look through these terms and find out where are we getting a beta squared. So how do we get such beta squareds? There will be no beta squared here or here, but this term will give us a beta squared times an a sub 2. And I write 2 choose 2 because there's really a binomial theorem, a very simple one being applied here to alpha plus beta squared. The coefficient of beta squared could be thought of as 2 choose 2. In this term here, the coefficient of beta squared will involve 3 choose 2. There will also be an alpha term because the total degree has to be 3. And the a sub 3, which is already there. Similarly, the next term, there'll be an a sub 4. The coefficient of beta squared will be 4 choose 2 times alpha squared. All the way up to the last term here, the coefficient of beta squared will be a sub n choose 2 times alpha to the n minus 2. And these numbers here are just the numbers appearing down that second column of the Pascal's array. The triangular numbers 1, 3, 6, and so on, up to n choose 2. So that's the proof of that second subderivative theorem. And here's an example. There's a polynomial p. Suppose we want to find its second subderivative. Then we go through each of these terms. We take one like this, for example. The 3 is lowered to a 1. And we have to multiply by 3 choose 2, which is 3. Here we have to multiply by 4 choose 2, which is 6. Here we have to multiply by 20 choose 2, which turns out to be 190. So that's how we take the second subderivative of the polynomial. It's a very good exercise to compare that to what you would get if you took the second derivative, which means take the derivative of p once and then take the derivative again. In other words, the derivative of the derivative. You'll see that you don't quite get this. You get a multiple of this. So the derivative of the derivative is more complicated because it has an extra factor. All the coefficients will be bigger than they really need to be. The important information is contained in the second subderivative. The extra complexity of the second derivative is most of the time completely unnecessary. Just extra baggage that students have to carry around. And the same remarks work for the third subderivative and higher subderivatives as well. These are more fundamental, more natural quantities than are the higher derivatives. And now we'd like to establish two basic computational rules for derivatives and subderivatives that tell us, first of all, how to calculate subderivatives for a sum of two polynumbers or polynomials, and then secondly, how you compute the subderivatives of a product of two polynomials or polynumbers. Addition is easier, so here's the addition rule for subderivatives. It's very, very simple. It's about as simple as it could be. It says that the kth subderivative of p plus q is just the kth subderivative of p plus the kth subderivative of q. And it's almost obvious, but let me write it out anyway, just to show you how these things can go. So the crucial object is the Taylor bipoly number. The quantity t of p plus q, which is p plus q of alpha plus beta. So if p and q are polynomials, then p plus q of alpha plus beta will be p of alpha plus beta plus q of alpha plus beta. So those are the individual Taylor bipoly numbers for p and q. So the information is already contained in this equation here because these Taylor bipoly numbers, they encode all the subderivatives. There are all the subderivatives of p plus q, there are all the subderivatives of p, there are all the subderivatives of q. And the statement that this thing is equal to this plus this just means that this equals this plus this equals this plus this, and so on all the way through. So for any k, the kth subderivative of p plus q will be the sum of the kth subderivative of p plus the kth subderivative of q. The multiplication rule that tells us how to find the subderivative of a product of polynomials, very important rule, is more complicated, but it's still pretty familiar, I hope. Here it is right here, saying that the kth subderivative of the product p times q is a sum of terms d0 of p times dk of q plus d1 of p times dk minus 1 of q, all the way up to dk of p times d0 of q. So in all these products, the coefficients add up to k. We look at the Taylor polynomial for p times q. There it is there, p times q of alpha plus beta. Well, that's going to be p of alpha plus beta times q of alpha plus beta. In other words, the Taylor poly number for p times the Taylor number for q. So this equality here is the crucial one that connects the subderivatives. There is t of p times q, the various subderivatives of p times q. Here's t of p, just the subderivatives of p, and here subderivatives of q. And we're told that this is equal to this times this. Now you should think about this as being essentially a polynumber in beta equals the product of this polynumber times this polynumber. So the theorem resolves by looking at the coefficients of beta to the k in both expressions. The coefficient of beta to the k up here will be what we want, d sub k of p of q. And how do we get powers of beta to the k from this product? Well, by doing the product this one times the beta to the k, this one times the beta to the k minus 1, this one times the beta to the k minus 2 down here, and so on. So we're taking d sub p from here and d sub k of q from the bottom. And then we're adding d sub 1 from here and d sub k minus 1 from the bottom. All the way up till we get to the kth one on the top and the 0th one on the bottom. So it's just the way we multiply polynumbers. This is a polynumber equation. And you should think about it as being the expression or embodiment of this relation between the Taylor polynumbers. Okay, very important formula in calculus. Very special case, still also important on its own, the case when k equals 1. Just the simple derivative of the product p times q, then there will be only two terms. Just this times this plus this times this. Coefficients of beta. So we get p times d of q plus d of p times q. So the derivative of a product is 1 times the derivative of the other plus the derivative of the first times the other. So a pretty famous formula for a derivative. And finally, here is a step up from that first derivative formula. Here's the formula for the second subderivative of a product. D sub 2 of p times q is p times d sub 2 of q plus d1 of p times d1 of q plus d2 of p times q. And it's easy enough to write down explicitly the formula for d sub 3 and so on. Okay, here's just some exercises for you to practice taking subderivatives and making sure that you understand how these addition and multiplication rules work. The addition rule, of course, is very simple, but still, we want to have some practice calculating subderivatives and verifying the various corollaries. And I suggest that you have a go with not just these ones, but you can make up your own polynomials, take derivatives, take products, take derivatives of products, and so on. Now that we have these tools at hand, we are in a position to do some interesting things. Next time, we're going to apply this very elementary approach to calculus, talking about tangent lines and, in fact, tangent conics to polynomials or polynumbers. This will still be done in a very algebraic framework, and we'll see that we're going to get some surprising results. Perhaps some lovely theorems that, even if you've been teaching calculus for many years, may be new to you. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.